everyone, I'm Ada, and yet I'm here again with another physics video. In this video we're going to continue with the general topic of kinematics, but we're going to cover the subtopics of freefall, parabolic motion, height, and range. So, what is freefall? Actually, before explaining what is freefall, let's get into explaining what the gravitational constant is. So, the gravitational constant, or showcased as small g, is a constant of acceleration, which is the same everywhere on Earth. Well, actually, not technically the same. This is just an approximation value. You can see it by a lot of values. It's generally showcased as 9.8 or 9.81. In the TIL exams, you'll most likely see it as about 10 meters per second squared. The reason for that is, well, it's practical to use in problems. You won't have a calculator ready with you in the exam. So, like I said, this is not technically a constant everywhere in the world, and I'm going to tell you about that stuff in later videos, but technically speaking, if you're going up, your gravitational constant is getting smaller and smaller. So this is just an average value we're going to use in our equations, the kinematic equations for constant acceleration that we learned in the previous video. So we know what the gravitational constant is. What is freefall? Well, freefall is, let's say that you have a body A and you're up in the air. You're near clouds, you're up in the air, you're near planes and birds and stuff like that. I don't know. I obviously can't draw good. So you have a body resting on air, and when we drop that, it will result in the action of what we call a freefall. A freefall is basically just having the gravitational force and no other force at all. Of course, for this case, we are neglecting the pressure that is going to be forced on the body from the air. We only have the gravitational force, and that is going to be equal to the mass of the body and the acceleration, which is the gravitational constant in this case. But you don't need to worry about what the force is. We are just working with kinematics in here. So we just need to visualize the acceleration, which is the gravitational constant. Let's solve a tiny problem. Let's say that we have a body A resting up in the air, and it's going to take an action of free fall with the constant g, which we can take as 10 meters per second squared for this case. It's high above the ground, let's say 250 meters, and we like to know in how much time it will reach the ground. Well, what we know that we don't have an initial velocity, and yet we don't know our final velocity. We don't know how much time it will take. We know the height, the distance, the displacement of the body, which is 250 meters. And we know the acceleration, which is 10 meters per second squared. Let's try to work this through together. How can we figure this out? Let's try to apply this formula. Our final velocity is equal to our initial velocity plus the acceleration times the change in time. This is, well, sure. From here we can figure out the final velocity. Our initial velocity is 0. Our acceleration is 10 meters per second squared. But we don't know the time. And also we don't care about the final velocity, really. I mean, we could use that in somewhere else, but why don't we just find it in a more direct manner? We can say that the displacement is equal to our initial velocity times t plus half of our acceleration times t squared. Now that works, because we know our displacement is 250 meters. Our initial velocity is 0, leading to this entire term being 0. Our acceleration is 10 meters per second squared. And from here we can figure out the time. This will lead to 5, and we can just divide that by 5, which is 50, right? Yeah, 50. And that's the square root of 50 meters, whatever that the solution to that is. I don't really care about that for this case. So that's freefall. Another topic that we are going to cover up in the air is projectile motion. Because we're not always in freefall while we are in air, we can have a starting velocity. We can have a starting position different from the top of our heads. And that is our type of motion called the projectile motion or parabolic motion. So our projectile motion would be something like this. If we had a body resting on the ground, and if we, let's say, kick it with an initial velocity, we can figure out a ton of things. First of all, we can figure out the components of the initial velocity, the horizontal and the vertical components. Why is that important? Well, because since we can't really deal with the singular velocity with our equations, it's easier to divide them by the horizontal and the vertical. What we know is that on the horizontal axis we don't have an acceleration at all. It's 0. Of course, again, neglecting the air resistance. But on the vertical axis, we have an acceleration of minus 10 meters per squared. The minus is, well, that's because I presume that the upward motion takes a positive sign and the downward motion takes the negative sign. This could be positive, but then the upward motion would have the negative. From this, we can define quite a lot of things. So first of all, let's define time. There are 2 important points in here. Well, technically 3. The starting point, the middle point, and the ending point. Let's call this point A and this point B. While we are in the top point, we will see something that because our acceleration is decreasing our vertical velocity, on the top point we won't have a vertical velocity at all. This is the point of a sign change. Our velocity was in the positive direction, and after this point it will start to be in the negative direction. This helps us in a matter of ways, because in this point we only have to deal with the horizontal velocity. Let's define a couple of things here on the top of our head. We need to call this distance something. Let's call it height. Let's give it a value of h. And what about how far the object went? I mean this distance. We call that range. So in a typical projectile motion problem, we have two variables that we are interested in: the height of the projectile motion and the range of the projectile motion. And we can figure both of those just by looking at their initial velocities and knowing the gravitational constant. What also matters in a projectile motion is obviously the degree. You might encounter that the 45 degree is most likely called the most optimum degree of choice, because you'll have the biggest range in 45 degrees. After that point, your height is going to keep on increasing, but your range is going to keep on decreasing. But if you go lesser than 45 degrees, both your height and range is going to keep on decreasing. So let's define these values. We have the initial velocity, and let's just call that v. The horizontal velocity, calling this angle theta, would be equal to v times cosine theta. And the vertical velocity would be equal to v times sine theta. To understand the time when the vertical velocity will be 0. Let's look at that. We have a tiny equation, and it goes something like this. The final velocity in this case should be equal to 0. And the initial velocity, as we know, is v times sine theta. We know that our acceleration is minus 10 meters per second squared. And this t will be RTA. Of course, the gravitational constant can be changed depending on the problem. So let's call this value g for the sake of definition. Now we can say that TA is equal to v times sine theta divided by g. We define TA as v sine theta divided by g. We can find what h is. We can say that h is equal to our initial velocity, which in this case is the initial vertical velocity, which is v sine theta, times TA minus half of g times TA squared. We can open that up a little bit, and we can say that v sine theta times v sine theta divided by g is valid, minus half times g times v squared sine squared theta divided by g squared is also valid. We can say that these two values cancel each other out, and we end up with something like, let's see, v squared sine squared theta divided by 2g's. That's our h. How about our range? Well, one thing you need to understand that we defined the time it took for us to get from this point to point A as TA. But the time it takes for us to get to point B from point A is also TA, which is an intuitive explanation, I think. I could prove it mathematically too, but I don't think you need it. Because when you think that the starting conditions will be the same as the ending conditions, you can see that the time it needs to take should be the same from this side of the projectile motion and on this side. Using that fact, we can define range by saying this. We can say that range is equal to our initial velocity, which is v cosine theta, the horizontal initial velocity, times 2ta. And we don't have anything else because we don't have an acceleration in the positive side or on the negative side. This is the horizontal axis. We can open that up a little bit though, and we can say that v cosine theta times 2 times v sine theta divided by g is equal to our range. The thing is, you don't really need to know these equations from the top of your head, because as you can see from the beginning of the video, that I could just derive these equations in a matter of time. Because even though these are projectile motion problems, they are still kinematic problems in 2D space. We're using the same formulas, nothing has changed. We are just defining different things from the top of our heads. If you need them, and if you think that these will come in handy on problems, which is really not needed in many cases, you can try to memorize them, but I believe no need. And that's the end of our video, and see you another time.